Okay, we're going to go ahead and get started. So it's my great pleasure to introduce Nick Scoville, who's a key scientific mentor, role model, and collaborator of my own, and more importantly, one of my dearest friends in the field. Nick did his BA and PhD at Columbia, where he was advised by Phil Solomon. His first faculty position was at UMass Amherst. When he was there, he was associate director of the Five Colleges Radio Astronomy Observatory. In 1986, he moved to Caltech, where he's currently the Francis L. Mosley Professor Emeritus. And during his time at Caltech, he was director of the Owens Valley Observatory. Nick is a pioneer of galactic and extragalactic observational astrophysics with a focus on the infrared, submillimeter, and radio regimes. He's worked on a broad range of topics, ranging from star formation and interstellar medium in the Milky Way, going to local ultraluminous infrared galaxies and up to high redshift galaxies, although more at cosmic noon, which these days is called low redshift. I don't think you've done anything at redshift 14, but I might be mistaken. Although we'll hear about POP3 stars. Nick has, one of his many notable accomplishments is that he was a leader of the Cosmic Evolution Survey, COSMOS, which has had essentially a measurable impact on the entire field of extragalactic astrophysics. Nick is the recipient of a number of awards, most recently the Henry Norris Russell Lectureship from the AAS. He gave a wonderful speech when he received that. I really enjoyed that talk. And so I've talked about Nick, all his great scientific accomplishments, but that's definitely not all there is to Nick. He's also an extremely interesting person with a broad range of interests. One of his primary side interests, I won't even say a hobby, I think it's more serious than that, is metal sculpting. And I hear that occupies a lot of his time these days. And besides being recognized for his many scientific accomplishments, Nick is also famous or perhaps infamous for being the only Caltech professor that participated in the Doodah parade. So I'll let him tell you more about that interest. All right, Nick, please take it away.
Can you hear me? I thought I pressed that button. Okay.
Oh, and sorry, I should have mentioned Nick said he's happy to take questions during the talk, so he'd like
to. Yeah. So let's see. Is Julianne here? Not yet. Well, we'll roast Julianne when she gets in, because she was actually one of my participants in the Doodah parade. How many of you know what the Doodah parade is? Only friends of mine. In any case, it's a parody of the Rose Parade, which is held, of course, every year in Pasadena. And is this Julianne? No, we're about to get to you. So Chris, unfortunately for you, mentioned the fact that I participated or used to organize a group for the Doodah Parade, which is a parody of the Rose Parade. And you, in fact, were a central figure of our best act. We would always crash the Doodah Parade as it got started, that is, not properly entering it. We would just rush in after the first couple acts, which came down the street. And the Rose Parade itself is really kind of stuffy and careful and conservative. And the idea was to basically parody the Rose Parade. And the act which we had the year that Julianne participated was, if I may mention Julianne, it was, there was a series of 7 children born called the septuplets. Some of you may be old enough to remember. And it was a successful delivery of 7 children. So we decided we would make fun of this. And Julianne I nominated to be mother of the septuplets. And then we tied a painter's cloth around her waist. And the rest of us got underneath the painter's cloth and sort of, made motions like we were bouncing around. and we were tied with clothesline rope to Julianne. How much of this do you remember? Yeah, push harder, push harder. And then at that point, you know, after we'd been under there long enough, we'd roll out on the street with clothesline attached to Julianne. And this went on for probably about 5 blocks of the doodah parade before we got sick of it and stopped. But anyway, it was a great act and good fun. And nothing improper, I don't think. No, certainly not. Not Julianne. So what I want to do today is to cover a lot of the work which was already covered in the Russell lecture, but sort of updated. And Mike, the sound is all right. Is that correct? Okay. So what I'll do is cover a lot of what was in the Russell lecture. But, you know, when you get kind of to my age, you get kind of philosophical about the field. And one of the things that most amazes me is that in the last 100 years, we've gone to an epoch where there was actually a debate about whether there were any other galaxies. Remember the island universe debate, and the so-called Curtis and Shapley great debate in 1912, I think it was, in 1922. And now to the point where people are routinely producing catalogs in Cosmos. We have, you know, 1 million galaxies observed in the 2-degree region of the sky. And we're looking all the way back to redshift 10, roughly. And so, you know, it's absolutely amazing to me that we've gone so far. We've not only, you know, increased the depth of our view, but also multi-wavelength capability of observational facilities and numerical simulations like those done here enable us to really understand in detail all aspects of these galaxies. And, you know, think of it, only in the last 50 years did we have any observations of molecules in galaxies, the primary star-forming gas, and a number of other things. So, you know, it's quite amazing that it could happen in such a short space of time. And I sometimes get a little bit emotional about it. I've been here in a lucky time, and you sort of think that, you know, maybe the young people won't have anything else to do, but they keep finding things we did wrong, or they also find that the field is much richer than we in our superficial initial analysis realized. And, you know, it's wonderful to see problems continue to, you know, come up to the top and for people to work on those problems. So the first thing I feel like I really should do, oops, what happened there, is honor, and I never knew him, Jim Simons, who obviously started this institute, and you all know of him. But, you know, he's a model for both public, well, for private funding of science. And it's really wonderful to be here for basically the first time I've ever spoken here. But unfortunately, tragically, you know, a week after his death. But he's an amazing person who has, you know, greatly stimulated science in not only astronomy and astrophysics, but in other fields of science. And I also have invited a number of family and friends to come, and just so that everybody's on the same page, because, you know, I've given a talk before where I referred to redshift, and it turned out that, you know, some of my friends didn't even know what redshift was. So let me just quickly go through that and bore the people who all know this. But, you know, astronomers measure distances at parsecs, which 1 parsec is the distance as the Earth goes around the sun. The image of the star in parallax shifts by 1 arc second. 1/3600th of a degree. And a parsec, which, you know, I prefer actually use light years, is about 3 light years. So then the other thing which is used all the time is redshift, as I mentioned. And it's basically the length scale factor for the expanding universe. And so the actual universe relative to the present day has a scale at a given redshift of 1/1 plus z. So for example, at redshift 6, about 1 billion years after the Big Bang, the redshift was on the scale of all distances in the universe, including the distances with photons coming to us, are reduced by a factor of 1/7. So, you know, it comes up throughout astronomy. And higher redshift obviously means greater distance from us. Redshift 0 is present day. But the other wonderful thing, of course, is that you all know, is that as you go to look further out, you're looking back in time. And, you know, instead of having a laboratory that you go and dunk your head into and get, you know, pick up fevers and whatnot, all you need to do is do deeper exposures going out to larger redshift, and you're looking back in time. You can see evolution in time. And that's basically what this talk is all about. So is there evolution in the universe? The primary, you know, observation of evolution was the initial discovery of quasars, which was in the late 1960s. And those quasars, you know, looked like their distribution peaked at around redshift 2. And the same thing, it turns out, is the case for the amount of star formation in the universe per unit volume in the universe. It peaks at redshift 2, which corresponds to about 4 gigayears of 4 billion years of cosmic age. So this is from a review article. So the talk will actually be in 3 parts. One dealing with insights from nearby galaxies, because I think, you know, it behooves everybody, if you're going to study galaxies at redshift 2 or 3, you really need to understand what's going on in the galaxies nearest to you. And obviously they've evolved a lot from redshift 2 to 3 down to the present, but you should understand the physics of what's going on in the gas in the present galaxies. So what these insights will deal with is what actually triggers star formation. And I think, you know, I'm going to take a poll and ask people in the audience, particularly the astronomers, is, you know, what their view of what actually triggers star formation is. So that the overall evolution of gas is the subject of this particular talk, but the gas is critical to the evolution because it's the interstellar gas which will form stars in the future and has formed stars in the past. But then also, it's the interstellar gas behaves very differently than the stellar population. The gas is dissipative. So when 2 gas clouds collide, they will, you know, have shock fronts, which then convert kinetic energy motion into radiation or cooling of the kinetic energy of motion. And it's very different, of course, than the stars interact, which is largely just gravitational interactions at long distances, and not much dissipation of energy, but redistribution of energy. So as I say here, it'd be good to make the discussion interactive. And then the final subject will be, which I became interested in about a month ago, is population 3 star formation. And I have a few sort of random thoughts about that. So what do these gas clouds look like? And this, of course, is an image of the Milky Way on a dark night, I think taken from out in the desert near Los Angeles, not by me, but showing these the Milky Way is actually not just a single band of stars, but two bands of stars. In the middle between those two bands is this dark area, which turns out to be interstellar clouds of dust grains, which absorb the light from more distant objects. And so it's those dust grains, those dust clouds, which contain also gas, and it's the gas which is the active ingredient in the universal evolution. So within these clouds, 99% of the mass is gaseous, mostly molecular hydrogen gas, but small trace amounts of CO and other molecules. And about 1% of the mass is dust. So we're going to use the dust as a probe of the mass of clouds at not only nearby environments, but also at high redshift. And the dust grains are a tenth of a micron size, solid particles, which are mainly made up of graphite, meaning carbon, or silicates, magnesium, iron, silicate, dioxide. But these are very small. And the amazing thing is that these dust grains by particle are only 1 part in 10 to the 11 of the number density of the gas particles, the molecular hydrogen. And so that means that if you take a typical line of sight through gas where it's, say, 1 atom per cubic centimeter, and I bet you most of the people here don't realize this, if you have to go from the initial place where you see a dust grain and an atom, you have to go something like 100 kilometers in order, I think it's several thousand kilometers before you get to the next dust grain. So that sparse distribution of dust is what's blocking the background light. And it attests to the fact that these clouds are really enormous. They're typically 10, 20, 30 parsecs in scale. And you can see their structure is very irregular. It's not spherical. They're filamentary. Feel free to ask questions as they go along. So here is a view which the astrophysicists here have all seen probably, but showing the distribution of H1 as you look at the Milky Way, atomic hydrogen, molecular hydrogen. You can see quite different distributions. The molecular hydrogen is more concentrated towards the center of the galaxy. The center is in the middle of these images, which are scanning along the Milky Way. The radio emission is concentrated in the center. The far infrared, which is an indicator of the radiation absorbed from star formation and then re-radiated by the dust grains, which absorb that far infrared radiation. And then down in the bottom, there's a visual image. Okay, I think I need to speed it up a little bit. But if you look at the overall distribution of the different gas species, like the atomic hydrogen and the molecular hydrogen, that's what the solid curve there and the dashed line curve. Oops, I have to remember I do have it. Oh, God. Go back. I have an arrow key somewhere here. Ah, there it is. So here's the molecular hydrogen distribution, a function of galactic radius in kiloparsecs. And this is the molecular hydrogen distribution shown in the solid curve. And then the atomic hydrogen distribution is the flat curve. So the atomic hydrogen is the golden rule, which I think most people don't fully realize, is that when the gas surface density, as you look down perpendicular to the disk of the galaxy, when the gas surface density exceeds about 10 to the 21 atoms per square centimeter looking down through the disk, the excess surface density shows up as molecular hydrogen rather than atomic hydrogen. And there's as yet no proper explanation really for why it occurs at that sort of threshold, and conversion occurs at 10 to the 21. So hopefully somebody here will work it out. There have been papers written on it, but not satisfactory. Yeah. The dust is fairly uniformly by abundance mixed in with both the atomic hydrogen and the molecular hydrogen, although probably is a little bit higher in the molecular hydrogen, which is more concentrated in the disk of the galaxy. So the dust abundance relative to the gas is fairly independent of the phase of the gas, except when you get to the ionized gas, which I didn't point out, but is denoted H Roman numeral 2 here. Okay, so looking at one of these clouds in detail, and this comes into later parts of the lecture, here is a picture of the nearest so-called giant molecular cloud in Orion. And this includes data from Planck and from Herschel to get the infrared fluxes. And let's see, the well-known Orion optical nebula is this little region in here. This is NGC 2024 in the northern Orion cloud. And you can immediately see that the area where you see optical star formation is a very small fraction of the overall extent of the cloud. Over in here, there's dust, which is warm, but not very warm, meaning it's dust at temperatures of 25, 30 degrees Kelvin. And then the dust on the immediate boundary of the Orion Nebula might be at 100 degrees Kelvin at most. So, you know, the dust, well, it's too bad that maybe this computer is telling me something, stop using that arrow. In any case, the two different Orion clouds have velocities that are separated by about 3 kilometers per second. And so if you look at them, it's an entirely reasonable scenario is that these two clouds have passed by each other. Some gas has been compressed as a result of the bulk motion of one cloud relative to another through shock front compression. And then now they're sort of going off after that separation. But notice that the two areas of rapid star formation are in the adjacent parts of the two separate clouds. So it looks to me, at least in my semi-theoretical imagination, that in fact the gas has been triggered into star formation as a result of these two clouds colliding with each other. Okay, so here are the questions for the audience, and some regard paradoxes. If we work up from the bottom, how long-lived are these molecular clouds? Do they last forever? Do they last 10 million, 20 million, 100 million years? Why is there any gas left? Because if you take the overall rate of star formation in our galaxy and divide that into the total mass of molecular gas, star-forming gas in our galaxy, you end up with a number which is about 1 billion years, whereas our galaxy is roughly 5 to 10 billion years old. So why is there any residual gas left over? And that requires, obviously, some accretion over time. But then there's another, that's this calculation. But then if you look at the internal dynamics of the molecular clouds, they have supersonic motions, which are, you know, Mach 10 or so, 10 times the speed of sound in the gas. So why doesn't that motion get dissipated rapidly? And the crossing time within the clouds of those motions is typically a few million years. So how is it that you still see these motions? What energy source is maintaining those motions? Okay, so here's, one of the more beautiful galaxies, M51, which you've probably seen in many lectures, the Whirlpool galaxy. You see these beautiful spiral arms, and astronomers call this a density wave in the disk. That is, you can't have the same gas concentrated in the spiral arms over a long period of time, because otherwise, given the rotational motions you see in the disk of the galaxy, the arms would be wrapped up into a very tight series of circles around the nucleus of the galaxy. So what you actually see in these galaxies, the motions are like a wave on water, where not the same atoms are in the wave peaks at each, as a function of time. So since we're in the era of JWST, and everybody wants to see at least one JWST image in every astronomical talk, here is a comparison of M51 in HST imaging in the optical, and JWST continuum imaging in the near infrared and mid infrared with NIRCam. And you can see incredible detail and a lot of filamentary structure in the gas and dust. You're seeing the dust emission in both cases, dust emission between the spiral arms. And it was sufficiently different that I actually, taking these two images, couldn't align the photographs. So, there's probably different rotation in the photographs. And, despite the fact that they said what the, west and south were in the images where I grabbed these, it didn't make any sense to me. So I just put a little admission on the part of the speaker. Okay, so here is M74. Oh, let me back up to these questions. So let me see hands. The lifetime of these molecular gas structures, how many think it's 10 million years? Good. See, I'm doing this partially to prove to you that there's something worthwhile in the talk and you learn something. Okay, how about 100 million years? You're wrong, Chris. Depends on the cloud. No, I mean in total. I don't mean you catch it 1 million years from the end of the cloud.
But depends on the local. No, yeah, that's what I mean.
I don't believe you guys. Okay, so let's see. Why is there any gas left? So let me first of all deal with this. So suppose you draw annulus on the centered on this galaxy M74 and look at the gas circulation as it goes around in the density wave. If you're at a galactic radius in the galaxy where the molecular gas is dominating atomic gas, you can't then have a picture in which you have atomic gas and all the space between the spiral arms and the molecular gas concentrated just within the spiral arms. So the fact that the molecular gas density of these inner radii of the galaxies, like what you saw in the Milky Way, that density, that mass exceeds the atomic gas density, implies that the molecular gas clouds gas must be distributed in some way also into the inner arm regions. You can't just have it concentrated in the spiral arms, which I think was everybody's prejudice when they first looked at these dense molecular clouds. So the orbital time for the gas to circulate in the density wave, typically between one arm and the next arm, is about 100 million years. And so that implies that the gas remains molecular at least 100 million years, but not necessarily as the same gas structure, just that the phase of the gas is the same. And it may well be that bigger clouds are produced, or accumulate in the spiral arms and then separate when they come out of the spiral arms, but remaining molecular. Okay, so I know I'm using way too much time. So here's a nice paradox. That is, if the molecular gas is really distributed largely, in both the arm and inner arm regions, why on earth do you see the most rapid star formation, these little pink dots, which are ionized ionized hydrogen? Why do you see those dots lining so neatly along the spiral arms? See if any of you think fast. Based upon the image that you saw of the molecular clouds. O'Brien, for example, Chris. Oh, Chris, I never know what you're thinking when you. Yeah.
The density is much higher in the spiral arms.
Oh, the density is higher, yeah. But what are you going to do with that? Yeah, right. Yep. So that is what you really care about, is if you believe that maybe most of these massive clusters are formed by collisional compression upon collision of two clouds or multiple clouds, that occurs more rapidly in the spiral arm region and more frequently. And so therefore, if you're just at the borderline threshold for forming massive clusters. But then the other issue is why doesn't that occur? Why don't you convert 100% of the gas into stars? And I think there the answer is that if you look at those images of the star-forming clouds, they're filamentary. And so when two clouds collide, they don't necessarily collide edge to edge. And therefore the collisional compression going through the whole body of gas, but rather maybe like that. And so there's some point of interaction where you get collisional compression, as you saw in the Orion image. That's just my only possible explanation. Okay, so let's move on a little bit more rapidly. Oh, I'm going the wrong arrow. Never invited an older professor to give a talk. Okay, so suppose you want to evaluate the gas masses in these clouds. And the common technique at low redshift has been to look at carbon monoxide, which is a good tracer of the potential, of the mass potential within the individual clouds, and look at the 1 to 0 line. And we back in the early days found good correlation between the virial mass estimated from the line widths and sizes of the clouds and the mass determined by the column density of dust, scaling up by a factor of 100, the dust to gas ratio. So that unfortunately is a real problem for ALMA at high redshift, because when you go to the lowest observable frequency of ALMA is about 80 gigahertz, and the 1 to 0 line, which is well calibrated as a mass tracer of the molecular clouds, is at 115 gigahertz, and so you only can go out to redshift 0.3, 0.5 or so, and still observe the lowest calibrated line of CO. Okay, so there are other problems, and I'm not going to belabor it. So what I want to do is describe a new technique which I've developed and other people have used. That's on the basis of understanding the dust emission spectrum. So let's get the arrow back. So imagine that you have a very simple-minded picture of one of these star-forming clouds as being spherical with a cluster of stars. It could be a galactic nucleus. It could be simply a massive star cluster in the center. And the radiation is then absorbed by the dust immediately surrounding that cluster. And then that dust is heated to a moderately high temperature and then re-radiates at longer wavelengths. and then successive layers of absorption and re-radiation degrade the radiation. So, you know, the initial shell immediately surrounding the ionized hydrogen region might be 500 degrees Kelvin, but then as you move out into the bulk of the mass of the cloud, the temperature becomes much lower, like 25 degrees Kelvin. Now, here is the reason why this happens is because if you look at the opacity coefficient for the dust absorption, you can see the highest opacity is certainly in the visible. And as you move out to longer wavelengths in the infrared, oh God, I hate this. Oh wait, you're not supposed to swear when I'm talking. As you move out into the longer wavelengths, the dust is much less opaque and in fact becomes transparent. So this means if you observe out in here, the infrared radiation from these clouds, you can actually see through the cloud, measure the total amount of dust emission, and add that up, and that tells you what the mass of the cloud is. So here are 3 radiative transfer models I did. Amazing, somebody like me can do radiative transfer, but and Chris would never believe it for sure. Well, anyway, so in these 3 models, what I have is a single source of luminosity at the center of that circular spherical cloud, and then vary the mass of the overlying dust with the same 1/r dependence away from the central source. And the lowest dust mass cloud has an optically thin mid-infrared tail out here. These would be the wavelengths observed by JWST. And then as you increase the dust mass by a factor of 10 in these other 2 models, you see that the curve becomes absorbed on the short wavelength side. And so it's greatly suppressed radiation, but then on the long wavelength side, the flux on the Rayleigh Jean's tail rises continuously and directly proportional to the dust mass. So this is obviously an idealized model, but this is the technique which I use to estimate the mass of these high redshift sources we're looking at. In fact, here is the calibration plot where I plotted the long wavelength flux in the submillimeter, 850 microns, versus the ratio of the submillimeter luminosity to the overall mass of dust in those different models or in the observations. So these are clouds which, you know, 128 galaxies, which had both Rayleigh Jean's flux measurements and CO1 to 0 line measurements, because, you know, a few of these galaxies have been observed at the EVLA in the redshifted continuum with EVLA. Okay, so you can see very good correlation between the two, basically a factor of 2 accuracy, which for astronomy is kind of record accuracy, but not for theoretical simulation. I guess, you know, it's kind of unbecoming to insult your host, but we'll see. He'll attack me later, or his friends. Okay, so the observations were taken at the ALMA array, which most of you know is at 16,500 feet in northern Chile on the border of Bolivia and Argentina. And you don't go away from the observatory in their direction because there are buried mines along the road if you head over to the east. So in any case, it's at 16,500 feet, and there are 54 12-meter telescopes and 12 7-meter telescopes. And it's an incredible feat. I never thought it would work, but it does, and works quite reliably. And it's the facility we should have had 30 years ago. So just to prove that some of us old people can survive at 16,000 feet, took a picture of Jacqueline Bergeron. Anybody here know Jacqueline? She's a hardcore smoker, and sometimes myself, and then Dave Sanders and Dieter Lutz. Yeah. Okay, so the logic of this analysis, which, here we have some scientific content at last. The gas masses are derived from the long wavelength continuum flux as observed at ALMA. I went to the archive for ALMA and simply pulled out other people's data, which is allowed, and measured the continuum flux myself, and did that at places where there was a Herschel detected source, meaning far infrared luminosity, and that was used to derive the star formation rate from the dust embedded luminosity, and then derived another quantity, which is I call the star formation efficiency, which is the star formation rate per unit gas mass as derived by these two measures above. And we explore the dependence of gas mass, star formation rate, and star formation efficiency on both the age of the galaxy, the cosmic age, the stellar mass of the galaxy you're looking at. Is a sample of 700 galaxies, which is really quite incredible at high redshift. And whether the galaxy was on the so-called main sequence of star-forming galaxies or above or below the main sequence. So all these are parameterized in this fitting for the 700 galaxies over the range 0.5 to 5 in redshift. So here are the data points for example, the gas masses derived from the Rayleigh-Jeans continuum versus redshift for all the sample of galaxies. And you can see there's very systematic increase in the gas masses as you go to earlier redshift, as you would expect, because galaxies started off with 100% gas mass and then have been using that up and forming stars. And also there's been further accretion to those galaxies, increasing the gas mass and going in the opposite direction. So the amazing thing is here, these galaxies get up to 100 billion solar masses, whereas the Milky Way, the present gas mass is only roughly 2 billion. So a factor of 10 to 100 larger gas mass in these early cosmic epochs. So it's actually, it surprised me that you could get up that high in terms of gas content in the early universe galaxies that you observed. So in the subsequent plots, what I'm going to show is, rather than plotting every data point, I just plot the mean and the dispersion in the points as a function of the variable redshift in this case for both the gas mass and the star formation efficiency here. And you care about star formation efficiency because you wonder at high redshift, are these galaxies more star forming simply as a result of having higher gas mass, or are they converting the gas to stars more efficiently per unit time? Okay, so then the other thing is, how does this dependence of gas mass and star formation efficiency depend on the stellar masses of the galaxy? Stellar mass evaluated from the optical spectral energy distribution of the source. And basically, you find that the gas mass is fairly independent of it's more modestly dependent on the stellar mass, and the star formation efficiency basically independent of the stellar mass of the galaxy. So what would be a possible physical interpretation of that? Thinking out loud for a second. Any ideas? Well, unfortunately, as mentioned down below, suppose that the clouds are self-gravitating as we think most molecular clouds are in local galaxies. If they're self-gravitating, they simply don't care what the nature of the galaxy that they're inhabiting is, because the gravitational field is cut off from the larger galaxy. So I think that's one possible interpretation. It's probably not the unique one. I'm sure the clever people here will come up with a bunch of other explanations. Okay, so then the other issue is how about whether a galaxy is on the so-called main sequence of star-forming galaxies, or above it or below it. And here's that dependence. And you can see that basically the gas mass increases a little bit as you go above the main sequence over here on the right. But the increase is fairly modest. And then the star formation efficiency is the dominant change as you go above the main sequence. So, I sort of view that as indicating that possibly that when you go above the main sequence, it's galaxy merging, which involves a lot of collision of gas parcels in the galaxies, which is increasing the star formation rate. Okay, so then the other thing we can do with this data for 700 galaxies is simply measure the overall cosmic mass density, both in non-star forming galaxies like elliptical galaxies, reddish galaxies without much active star formation, stars and star forming galaxies, and gas in those galaxies. And so the significant thing you can see is that the gas content of these galaxies per unit density, co-moving density in the universe, actually rises over cosmic time as you get to older and older epochs, all the way down to approximately redshift 1.2 or 5.9 gigayears after the Big Bang, and then gradually falls off as the star-forming galaxies use up that gas. But it tells you that the galaxies were not dominated by the stellar mass, which every optical observer would like to tell you about, but rather the overall gas content is dominating the mass content of these galaxies, all the way down to redshift 1 almost, which is quite phenomenal. It surprised me, actually. So then if you look at the evolution of baryons, the gas mass fraction compared to gas plus stars, you can see that here, once again, you come all the way down to about 1.8 or so redshift, or about 4 gigayears of cosmic time, where the gas is dominating the overall mass content of the galaxies. So in summary, here's the list of the conclusions from this first part, and the second part will be mercifully short. The gas dominates the stars all the way down to redshift 1.2. The increased star formation in the early universe is about 2/3 due to higher gas masses in those galaxies, and about 1/3 due to increased star formation efficiency. For starburst galaxies above the main sequence, 2/3 of the increased star formation rate is due to higher star formation rate per unit gas mass, and 1/3 due to the higher gas content. And then this I haven't described, but you can evaluate what accretion rate, and Avishai would probably be interested in this, what accretion rate is required to keep these galaxies still going with their star formation rate. And I get a similar number to what Avishai has in an analytical treatment, but it's actually maybe a factor of 2 higher, but in astronomy, I don't consider that a bad error. So you can describe how that's done later, but it's the accretion rate, not that is observed, but which is actually required to maintain the galaxies on the main sequence as it evolves in time. Okay, so what? Plus recycling, yeah. I mean, I include the recycling also, the amount lost from stellar mass loss as the stars evolve. Okay, so now the last, which is just very short, is population 3 galaxies, which I know nothing about, except I read a paper, a review paper by Volker Braun, which is an analytic treatment of models for mini halos at redshift 20 to 30. All the galaxies I've been talking about so far have been redshift out to 5, but no higher than 5. But redshift 20 to 30, 180 to 100 mega years after the Big Bang, which is incredible. And theoreticians always have quite incredible imagination. So, you know, you get curious about it. So the models which I took include a mini halo of mass 10 to the 6 solar masses of gas with hydrogen and helium, starting out with the primeval abundances. Primeval abundances, and then at that point, it's say redshift 20 to 30, the universe was 10 to the minus 4, 10 to the minus 5 smaller. So the smaller volumes means a much higher density in the gas, which is collapsing to form these population 3 galaxies. So in looking up in the literature, and I may be wrong, but I couldn't see any handling of the possibility of dust in these population 3 proto-galaxies. And the obvious reason would be that, you know, they're dealing with a primeval gas supply, which is largely hydrogen and helium, and no heavier elements. But in fact, the first few stars to form in a given population 3 mini halo will produce dust as a result of AGB mass loss and supernova explosions within of the order of 50 to 100 million years after the formation of those first stars. And so that dust then ejected into the halo, mini halo environment can form dust grains, and who knows how much dust, but you know, I in the models that I did, I assumed that that the dust metallicity or dust to gas ratio was 10 to the minus 4th of what it is in the solar neighborhood. So going from 100 to 1 gas to dust ratio down to 10 to the minus 2 gas to dust ratio is what I did. And then if you calculate, take this opacity curve, which I had from drain, and then translate it into that mass of dust, it turns out that those mini halos will be optically thick all the way out to this point here, meaning 1 millimeter wavelength. So that's something which I may be wrong, but I haven't seen discussed in literature of population 3 galaxies at all. And it obviously would limit the amount of radiation you could see in the rest frame, visible or UV. And most of the searches, for example, with JWST, even at these redshifts, the rest frame UV will be shifted into the long mid-infrared. Okay, so I think the overall summary is here. And I got into the population 3-star business because I asked a question in somebody's seminar at Caltech that, what about the radiation pressure of the CMB, which is much hotter at those redshifts, acting as a compressive force on the gas distribution in the mini halo. And so I calculated that, and it seems to me that it's a factor of 10% or so of the raw gravitational acceleration. So I view that as not an important effect, but I also could have made a mistake, God forbid. So let's see. Anything else I needed to mention? No, I don't think so. So let me stop at that. Am I on time? That's the first time I've ever been on time. Okay. Thank you all very much. Everybody's stunned or asleep. It does happen occasionally, even in New York City, people sleep, but not during a seminar, for heaven's sake.
So I was curious, Nick, since
Yeah.
you mentioned, and you put on the summary slide here, that the starburst above the main sequence, they're like the higher SFE is likely due to merging.
Well, just
elaborate on that. Do we actually see evidence, for it?
I think it's very difficult to identify whether some, occasionally you will see the two separate galaxies and infer that they're close enough that there could have been interaction, but the tidal tails. But by the time that you really increase the star formation rate hugely, probably the two central disks have merged and blended in together. So I think actually using observations to identify those galaxies is not very easy or reliable. They could be identified, for example, from C2, carbon 2 spectrum. She's doing that, I think, in some cases, maybe. But there's not enough 154 micron or 158 micron carbon 2 observations. That's a good way to get dynamical masses and also identify separate dynamical. Yeah. Yeah.
Sorry, could you just press the button on your seat on the right there?
And you get ejected from the auditorium.
There's a microphone.
Yeah, what happens is.
Oh, I could just yell. Oh, okay. I just cosmologists talk about cold dark matter forming early galaxies and blah 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 blah. I mean, is that important? You didn't say anything about that.
No, I didn't.
I mean, I don't know if it matters. I'm not in the field, right? So
maybe somebody else. There are people who do the simulations with the cold dark matter and without. So anybody want to?
Okay, it doesn't matter.
No, it does matter.
Yeah.
I mean, I can.
It's complicated though.
We can. That's a good topic for better discussion also.
Okay.
But basically, when you run a cold dark matter simulation, the dark matter dominates up the baryon, and it's setting the overall, like the large scale motion, that's the dominant gravitational force coming from dark matter. And so when you run one of these dark matter simulations with the gas in there, you get the galaxy so-called halos are collapsing and dragging the gas along. And what we see is if you look at one of those simulations, you see the kind of gas accretion rate that Nick infers that you need from the observations to maintain the star formation rates in galaxies. So essentially in the simulations that have this cold dark matter paradigm, you end up getting results that are consistent with these observations. So we believe that it is a very important part of galaxy formation, and it gives you results kind of consistent with what it is.
Let me just quickly show something which addresses the accretion rate, which Avishai has worked on. So what? So if you look at what's shown here is the main sequence evolving as a function of time, going down in terms of star formation rate at a fixed stellar mass. And the dashed lines are the evolutionary curves, which would be implied in terms of star formation rate per unit mass as you progress in redshift. So then the accretion rate, which I derive in the next plot, which I'll show in a second, is equal to 0.7 of integrating the star formation rate along each one of these lines. Along each one of these lines as you come down in redshift. And then requiring that only, at 30% of the star formation rate is ejected back into the galaxy. And then that the required accretion rate is given by the comparison of what gas mass you end up with at the end of this progression. And the accretion rates are shown here. And this is actually in the 2023 paper. The accretion rates are shown here. And you can see they're enormous and about a factor of 2 higher than the ones which Avishai calculated analytically. And who knows? And, one shouldn't believe the main sequence curves too closely either. But, okay.
I was just wondering, what do you learn by looking at different locations inside the local galaxies or inside the Milky Way even? Because my understanding is that at the center of the Milky Way, the densities are much higher and the star formation is probably proceeding at in a very different way from
well, you do see in the galactic center enormous not enormous physically, but very high levels of star formation in a few giant molecular clouds. For example, Sagittarius B2 and Sagittarius A cloud and Sagittarius C. They can have star formation rates more than any other cloud in the galaxy, but not factors of 10 more. But at the high end of the luminosity distribution in the infrared. I myself think that any star formation rates estimated without infrared measurements are very unreliable. But the structure in the center of our galaxy is dynamically modeled often now as a bar potential. And along that bar, there will be places where there's shocking of the gas within the bar. I'm not sure I'm really getting to the gist of your question. You gave up. Sorry. Maybe speak a little louder.
Sorry, just press the button.
Yes. So you mentioned about star formation efficiencies in 2 environments, and the first in nearby galaxies in-term difference. And you sort of, or Chris indicated that it's the density that changes star formation efficiency. And when you say density, it's the density within molecular clouds, or it's the density of molecular clouds, or the number density of molecular clouds? Which do you?
I have no idea what the number density is within the clouds, because they aren't resolved for the most part.
But is it the number density of clouds, or the density within clouds?
I think I'm referring to the mass of material, which is in molecular phase. But I passed by, you gave me an image, which was a beautiful image of M83 mapped with Alma and complete flux recovery. I skipped over that so quickly that nobody here appreciated it, but this beautiful work by Coda.
All right, so...
Oh, wait, let me just say. So Patricia Daly, who is actually a professor of comparative lit at Columbia, Here's a picture she took of the welding projects, which, you know, it's the best picture I have. And it's a fish with two perforated sheets, which as it rotates, you see these moire patterns. So it looks like the scales of the fish. But in this particular picture she took, it shows the fish hanging from the clouds. And it's beautiful. I wish I had a movie like this. But since that time, this fish has fallen many times and gotten dented. This was made in collaboration with Dan Gazzari here. It's gotten dented, and so I've now retired it to the repair shop or the garbage dump, but I'm making another fish. Okay.
All right. Well, let's thank Nick again, and we have questions.